Okay, let's wait a little longer. No, we can start. It's 4. Okay, welcome everyone. It's great to see you. This will be our last talk of the semester. Zach is going to be talking about subregular W algebras. Zach, feel free to start whenever you're ready.
All right, thank you, Flor, for the introduction, and thanks everyone for coming along. So as this kind of concise title suggests, I want to talk mostly about subregular W algebras today. So in particular, these W algebras in type A. So some of this is some joint work with my PhD supervisor, David Rideau, but let's get to it. So the outline for this talk is roughly as follows. I'll make some brief motivating remarks. I'll define the central objects of study. I'll talk briefly about, not briefly, I'll explain this idea about moving between W algebras by some kind of inverse reduction. I'll go through this inverse reduction with some subregular examples, and we'll get to the first result. And this first result is essentially this inverse reduction for type A subregular W algebras in both the universal and simple cases. Then I'll use this first main result to do some physics. So we'll talk about modularity and fusion rules for logarithmic conformal field theories. I'll go through some subregular examples to see what these things look like. And then we'll get to our second main set of results, which is essentially this data, or some of this data for subregular W algebras using this inverse reduction. And then I'll describe some future directions of study in this area. So as a lot of you know, just briefly say some things about physics. So when we talk about the kind of VOA content of a conformal field theory, we need a choice of vertex operator algebra and a category of V modules satisfying some conditions, whatever they may be. And when the C is semi-simple, we say it's rational. So we say the VOA, the CFT is rational. And what ends up happening is that a lot of the rational conformal field theories and rational VOAs that we see in nature end up being related to affine vertex algebras at non-negative integer levels in some way. So there's some procedure to get to these rational VOAs from affine VOAs. And these affine VOAs are in a sense well understood or known. All the physics information has been extracted. There's some understanding of how to pass that information through these processes like cosets and orbifolds and the like. However, what's happened relatively recently is that many new applications of conformal field theory to problems in physics, such as this 4D 2D duality of Beam and Rastelli or Cardy's percolation, seem to require conformal field theories that must be non-rational. So these applications in their existence require that the C is not semi-simple. So either C admits reducible modules that are not indecomposable, or C has infinitely many simple modules. And unfortunately, there are not many well understood examples of these from a physics representation theory point of view. And what we anticipate is that just like the affine vertex algebras at non-negative integer levels, these same vertex algebras at admissible levels play a similar role in the non-rational case. So these admissible levels were introduced by Katsumoto. They're precisely the levels for which the characters of the modules of the affine vertex algebra have modular properties that are kind of suitable for physics applications in a sense. And these are hard. These admissible level vertex algebras are hard, but by doing these things kind of by hand for low rank G, so like SL2, OSP12, it's kind of clear that to understand these admissible level affine vertex algebras, we need to know something about quantum Hamiltonian reductions. And these quantum Hamiltonian reductions that we need to know about might be rational and they might not be rational. So in a sense, if we want to understand these non-rational admissible vertex algebras, we're probably going to have to deal with non-rational W algebras at some point. So we get to the kind of natural question, which is why non-rational W algebras, which is primarily what this example ends up being. In a sense, we know quite a lot about rational W algebras, or not everything, but we know a lot. There's the regular or principal W algebras. We know fusion rules and everything else. There's the exceptional W algebras, which were worked out by Jethro Van Ecker and Tomoyuki Arakawa. However, there isn't really the same amount of depth of knowledge about the non-rational cases. And in particular, even just ignoring this whole relation to admissible level vertex algebras, these non-rational W algebras actually appear on their own in these applications. So in this 4D 2D duality, sometimes the thing on the 2D side is actually a non-rational W algebra. So kind of getting to grips with how these things work is important on its own, and then also from the perspective of affine BOAs. So as brief a definition as possible, because I'm sure a lot of you do know what these things are. So quantum Hamiltonian reduction, you give me a simple finite dimensional Lie algebra, a nilpotent element in G, and then a number K, which we call the level. We can do some homology to some chain complex, and we'll get a new vertex algebra, which we call a W algebra. And this process we call quantum Hamiltonian reduction of the corresponding universal affine vertex algebra. So given a G, if we take two nilpotent elements in the same nilpotent orbit, the W algebras will be isomorphic. But in principle, if the rank of G is large enough, there'll be a lot of nilpotent orbits. But one nilpotent orbit that always exists, or set of nilpotent elements that always exist, are these regular ones. So take a nilpotent element whose centralizer in G has dimension equal to the rank of G. These are called regular nilpotent elements. So understandably, we call the corresponding W algebras regular W algebras, which we denote by WKGF. And as is kind of tradition in this area, if we want to talk about simple quotients, we put K on the bottom. Now for SLN+1, which is again the type AN case that we're primarily concerned with, we can write down strong generators using what's known as the Miura transform if we want to. These I'll denote as follows, and these have the following conformal dimensions. So these were actually the first W algebras that were kind of constructed in whatever way. I think the first one was the SL3 by Zamolodchikov. And these have a very long and storied history of applications in both physics and mathematics. So this is done to the extent that sometimes when physics authors say W algebra, they mean regular W algebra. That's the extent to which these things are so ingrained in the history of everything. So another example of a set of nilpotent elements that always exists. So given a G, there's always a regular nilpotent, and there's always a subregular nilpotent. And subregular just means that the centralizer has dimension rank G plus 2, which is kind of the next biggest centralizer. We call these subregular W algebras. And again, simple quotients, put K on the bottom. Now these can be given a set of strong generators, which we'll denote as follows. So these G plus and G minus, we want to think of as being kind of charged fields under J, and J is a Heisenberg field. And these U3s and UNs are just some other nonsense. These strong generators were first found, or I think were first written down properly by Naoki Genra and Toshiro Kuwabara. However, these algebras for SLN+1 were actually first defined by Feigin and Semikhatov, who, and once they defined these things, these W2N algebras, it was long suspected that this was precisely the subregular W algebra, but that was only proven a little bit later on by Naoki Genra in 2016. And as I kind of suggested, outside of these strong generators and a few other facts, like for example, if we pick particular pairs of G and K, much of the structure and representation theory of these W algebras is a bit of a mystery. So the way we want to unpack these, this is kind of the goal of this project as a whole, is to understand these subregular W algebras a little bit better. And the way we're going to do that is using the following kind of picture. So again, we're going to stick to SLN+1, so type AN. In that case, nilpotent orbits can be indexed by partitions. We can define a dominance ordering on partitions, and we can kind of use that to define an ordering on W algebras. And it looks like the following. We have always at the top of the ordering, we have the affine vertex algebra. At the very bottom of the ordering, we always have the regular W algebra. And what always happens is that the bottom of this ordering looks like regular, subregular, and then some other stuff. So as soon as n is greater than or equal to 5 or 6, this stops being a chain and it splits and becomes a bit complicated. And what's interesting about this chain is that if we stick to admissible levels at this very top level, at the top of the chain, when these admissible levels are what's known as non-degenerate, which I'll define at some point, the W algebra on the bottom, or at least its simple quotient, is rational. If we take an admissible level that isn't non-degenerate, so a degenerate admissible level, the regular W algebra, the simple quotient, will be 0, and some other W algebra along this chain will be rational. And these are examples. These are what's known as exceptional W algebras. And in both of those cases, the modularity and fusion rules is known. So in a sense, if we fix an admissible level at the top, we have this thing at the top is not rational, but if we go far enough down the chain, we hit a rational vertex algebra. So the kind of idea in this picture is we want to push this information at the rational point up the chain and get information about the non-rational W algebras sitting on top. And a related question is what are these arrows? So if we go back to this picture, we can think of this arrow from SL2 to Virasoro as Hamiltonian reduction. SL3 to BP is Hamiltonian reduction. There's a hidden arrow from SL3 to W3, which is also Hamiltonian reduction. So we could think of these partial arrows as kind of like a partial Hamiltonian reduction. This hasn't been defined properly for vertex algebras in full generality, but it's very strongly suggested by some finite W algebra stuff that this can be defined in a sensible way. And here we mean by inverting, we mean the following. If the F1 W algebra is above the F2, so there's an arrow from F1 down to F2, we're going to construct an embedding of the former into the latter tensored with a lattice vertex algebra. And the reason this kind of makes sense is that we want to think about this lattice vertex algebra as being the directions that are killed off by the partial reduction. So we're reconstituting the W algebra on top by restoring the directions that are killed off. So this is hard in general, but what we can do is we can make a good start, which is the very bottommost arrow, which I remind you all there's an arrow from the subregular to the regular. So we want to know, can we construct this embedding? And then also from a physics perspective, think about when this descends to simple quotients. So ask the question, when can we put K on the bottom on both sides? So to see how this inverse reduction works, we'll go to n is equal to 1, so SL2. So in for SL2, the subregular W algebra is actually the affine vertex algebra, and the regular is the Virasoro. And here we nail down exactly what our lattice vertex algebra is. It's this so-called half lattice vertex algebra. Essentially, it's just a two-dimensional lattice vertex algebra where you only take one direction in the one direction of vertex operators. So these C and D are isotropic, and we only take one isotropic direction for vertex operators. And as it turns out, for SL2, this can be worked out explicitly. It was first actually written down by Semikhatov in 1994, but later clarified and worked out in vertex algebra language by Drazen Adamovich. And the result is the following. If we take K to be non-critical, we can define a conformal embedding. So this is the embedding we had before, subregular into regular tensor of lattice algebra. And it looks like the following. H embeds into some combo of C and D. E gets mapped to E plus C. F gets mapped to E minus C multiplied by a bunch of things. And in this bunch of things for F, the only combinations of C and D that appear are kind of multiples of V or derivatives of V. And also I should say here that U and V have 0 OPE together. So that's kind of interesting. And additionally, in Adamovich's paper, he worked out that this embedding descends to simple quotients precisely when K is not a positive integer. So that, and we also recognize that when K is a positive or non-negative integer, it's actually rational. So in a sense, this embedding knows when the thing on the left-hand side is rational in a way. Now, returning to admissible levels, when we have what's called a non-degenerate admissible level for SL2. So that just means K is fractional and this denominator is greater than or equal to 2. We use this funny notation A1UV. We call these like SL2 minimal models, even though they're not rational. And we see that what we get is that this non-rational SL2 minimal model embeds into the Virasoro minimal model tensored with pi. So a more recent example is we take n is equal to 2. So at n is equal to 2, the subregular W algebra is the Vyshkovsky-Polyakov algebra, which I believe Anna Kontrakt spoke about here maybe a couple months ago, a month ago. That vertex algebra has strong generators J, L, G plus minus. Again, G plus minus have plus minus 1 charge onto J. And the regular W algebra is the so-called Homologikov algebra. So this is strong generators T and W of conformal dimensions 2 and 3. And pretty much the same kind of story. Adamovich, Kawasetsu, and Ritter in 2020 defined a conformal embedding. We take K to be not critical. J gets mapped to some combination of C and D. It's a conformal embedding, so the energy momentum field does what it needs to do. G plus gets mapped to E plus, G minus gets mapped to E minus, and the only C and D fields that appear in G minus are wrapped up in this field B. And B and A have non-zero, have zero OPE or regular OPE. And what was worked out in this paper is that this actually descends to an embedding of simple quotients, so we can put K on the bottom exactly when the level does not satisfies these two conditions. So in this case for Vyshkovsky-Polyakov, you can consolidate this condition into one condition, which is like 2K plus 3 is not a positive integer, a non-negative integer. But in this case, it's instructive to write it in terms of 2. So as before for the SL2 case, we use this kind of funny notation, this kind of minimal model notation. We have these non-rational BP minimal models, and they embed into W3 minimal models, which are rational, tensored with pi. And here a non-degenerate admissible level for SL3 is one particular, this is of this form. So to kind of generalize this to general N, we have to be a bit more clever. So for SL2 and SL3, you can kind of open up OPE defs in Mathematica and spend an afternoon and kind of force it out. But in this case, the OPEs for subregular are really complicated, and the OPEs for the regular are really complicated. So in this case, we need to use some further input, and the input is of the form of these screening operators. And these are first defined by Naoki Genra in 2016 in general. And the idea is the following. So we take a Heisenberg vertex algebra generated by, so this is for SLN plus 1, we have n fields. The OPE is kind of governed by the SLN plus 1 Cartan matrix. And we take a beta gamma ghost system. So here's the beta gamma OPE is 1 on Z minus W, and all the other ones are 0. Then what we find, or what Naoki found, is that when K is not critical, the subregular embeds into the tensor product of H and beta gamma, and this embedding can be precisely picked out as the intersection of these kernels. So we have some screening operators. These act on H alpha beta gamma, take the kernels of the screening operators, take the intersection, we get the subregular W algebra precisely. Now looking at this, it doesn't look like we've done much because it's not like the regular W algebra is jumping out at us yet. But as it turns out, screening operators for the regular have been known for an incredibly long time. As it turns out, the regular W algebra embeds into H as well, and the screening operators look like this, which is kind of suggestive because we see that the only real difference between the subregular screening charges and the regular screening charges is this beta. So if we could conceivably set beta equals to 1, we'd be reducing from subregular to regular. And that's precisely what this partial reduction does for subregular to regular. The subregular to regular is a kind of homological way to set beta equal to 1 in the screening operators. Because we can't just do that, because we have to grapple with beta as it exists, we want to absorb beta into the vertex operator and then have a think about what we can do from there. And the way we do this is by this so-called bosonization. So this was known by, or worked out by Friedman, Martinek, and Schenkar a very long time ago in physics. But the idea is that this beta gamma system actually embeds into a half lattice. And again, this embedding is singled out precisely by these screening charges. So and what's nice about this embedding is that beta gets mapped to e to the c, and this is a vertex operator. So if we compose the embedding from the subregular into h pi with, or h beta gamma with beta gamma into pi, we get an embedding of the subregular into h tensor pi. And all we have to do, the kind of cost of doing that is picking up this additional kernel, which corresponds just to bosonizing. And here I've defined some funny fields, alpha tilde, and we see the only real difference is this C term. And again, the C term just comes from bosonizing. So here we've really seen that we've absorbed C into a vertex operator. This kind of a construction was used by Kroetig, Genra, and Nakatsuka in 2020 when talking about some Heisenberg cosets, which is a very nice result. So essentially, maybe I'll save that for a second. Essentially, we see here that we kind of have the regular W algebra screening operators. But the problem is that we ideally want the regular W algebra screening operators to only act on a Heisenberg vertex algebra. The problem is that C has non-zero OPE with pi, so it kind of it twists the action a little bit with contributions from pi. But a result that I'm currently writing up at the moment is that we can define a vertex algebra isomorphism, and essentially what it does is it simply declares these alpha tildes it says these alpha tildes generate their own Heisenberg vertex algebras, and then it organizes the rest of fields into some other vertex algebra, which we call pi tilde. As it turns out, this isomorphism is so nice that this pi tilde is actually just pi again. So in a sense, we've kind of changed the basis of this tensor product H tensor pi so that these alpha tilde operators only act on the Heisenberg part. And because these alpha operators, or alpha tilde operators, only act on the H alpha tilde, and we know that the regular embeds into H alpha tilde with exactly these screening charges, we therefore can say that we have this embedding. So in a sense, imposing these first n screening operators says that the fields of H alpha must be organized into regular W algebra fields. This final screening operator, when we write it correctly under this isomorphism, tells us how we need to combine regular W algebra fields and pi fields to get elements of the subregular. So this says that this embedding exists, at least for non-critical level. We can now ask, like, what does this tell us? So what's the point if we can't do much with it? It's a fairly non-constructive thing, but we'll have a go at constructing some things. So we can write down some fields, I and j, and we can make some identifications. We can identify the field j in the subregular as some combination of c and d. This is a conformal embedding, which is nice. Again, g plus goes to e plus. Slightly more difficult is this g minus operator. In this case, we get the following closed form expression, and this is using these strong generators. I believe this one was actually worked out by Feigen and Semikatov, but I used the forms that Genra and Kuwabara worked out. And then, so what we see here is this g minus field. It's the field of the Miura transform. It's some combination of these I fields, which are kind of perpendicular to j, and we get e to the minus c. And then what we can also do is take these expressions. We have this, the only other strong generators are these u fields, and these u fields can be expressed in terms of the w fields from the Miura transform again. So that's kind of it for the embedding. Maybe we can do some representation theory, and indeed we can. So if we take M to be a regular W algebra module, so we'll say, I think I should say here, maybe a highest weight module or something, maybe just positive energy and Z graded. And we take these funny things, these pi negative 1 Gs, these are just certain pi modules, and they're kind of, really the only ones that are Z graded in positive energy, in a sense. These ones are kind of selected for us by this conformal embedding. Then if I take the tensor product, again, I think I should say here that M is a highest weight module. This tensor product is actually a relaxed positive energy Z graded module for the subregular. In particular, what we can see here is that J is just a complex number. So, and some other, this expression for G minus and G plus also actually tells us that these things are almost always simple. So in particular, we have infinitely many simple modules for the subregular, the universal subregular. Even better, if M is almost simple, so if all the singular vectors are located at the top of the module, it's the same, this tensor product is also almost simple. So that's kind of cool. And we have some kind of understanding of singular vectors and highest weight vectors. So there's some idea about degeneration points and other things, but this is currently being worked out now. We're currently working out now. So now we know this embedding exists using these screening charges. The next question is, well, we know K has to be non-critical, but what levels give us an embedding of simple quotients? We can obviously compose this with the quotient map, but we want to know when we can replace the subregular with a simple quotient. And the n is equal to 2 case was actually described in this seminar series by Adamovich a couple months ago. And in the n equals 2 case, the idea is that this embedding constrains the form of singular vectors to be of a particular form, g plus to the m, and then essentially the g plus g minus OPE constrains k. And so this kind of relies on knowing what the g plus g minus OPE is. We don't know, it's not really possible to write down the g plus g minus OPE completely for n. I think you might down a handful of terms if you want to. But essentially, this exact same approach in this case shows that the embedding descends if and only if k satisfies these conditions. So another way to think about these conditions, which is maybe a bit nicer than the way I wrote it up, is that k plus n is not a fraction of a certain kind. It's not a fraction whose denominator is an integer from 1 through n. Now, if we require here that k is at admissible level, this condition actually just says that the only admissible levels for which the embedding descends to simple quotients are the non-degenerate ones. And the non-degenerate ones are precisely the ones for which the regular W algebra is rational. So in a way, this embedding of simple quotients naturally picks out the minimal models for the regular. And we introduce this funny notation, this kind of minimal model notation. And we find that the subregular minimal model embeds into the regular minimal model tensored pi. This regular minimal model is rational, so it only has finitely many modules. They're all highest weight, and all the kind of physics content is known. But this embedding defines a continuous family of relaxed modules, just in the way of before. And again, we see that this subregular W algebra minimal model is probably going to be not rational because we have infinitely many simple modules. So to summarize this first kind of half of the talk, we know when this embedding exists for the universals. So that's when K is not critical. We know how to decompose the strong generators. We can do some representation theory. Again, there's some kind of structural knowledge about these modules that the embedding provides us. We worked out when the embedding exists for simple quotients, and then also can define some continuous family of simple modules for the subregular UV. So part 2, we want to use this embedding to do some physics. And knowing that this embedding exists, particularly for the simple quotients, kind of gives us a hint that we can do some physics. Knowing that we want to these subregular W algebra minimal models appear in conformal field theory, we do need to know something about the representation theory. However, the difficulty here is that because these are probably going to be not rational because we have infinitely many simple modules, even in a kind of mild sense, we have to be a bit careful with finding the module category and kind of extracting all the information out. However, the small cases of n equals 1 and n equals 2, which have been worked out explicitly, show us sort of how to proceed here. And the idea is the following. So this is what's known as a standard module formalism. It was introduced by Kreutzig and Rideau. It's not necessarily a prescription saying that this always works for log CFTs, but it's merely an observation that this is a very general approach that appears to give sensible answers in a huge amount of cases. And the idea is that we start with a module. So we have a vertex algebra, and we choose a module category that has a continuous set of some things called standard modules. And what we require is, there's a few things that we require that these standard modules satisfy, but the most important is that their characters are linearly independent. Then what is often the case is that we can compute an action of SL2Z on these characters, and we obtain an S matrix. So it's not really an S matrix because there's a continuous variable and we integrate. So it's more of like an integration kernel. Then what's often the case is that all other modules in this category can be expressed, have characters that can be expressed in terms of these standard characters. So if we want the standard characters form a topological basis for the span of characters. Then we can use a kind of a continuous version of the Belinda formula to obtain some growth and diffusion rules. So one technical issue here is that this module category is not semi-simple. So by passing from modules to characters, we lose some information about reducibility. So in essence here, we're actually just computing modular transformations and fusion rules at the level of characters. And that's precisely these so-called growth and diffusion rules. But then what often happens as well is that you can kind of, in a bit of an ad hoc way, think about when these growth and diffusion rules lift to genuine fusion rules. Sometimes these fusion rules end up showing you new indecomposable modules and stuff. So this has been checked in a lot of cases. And in the cases for which you can kind of directly hack away at these things, has been shown to be correct or not wrong. And we want to know, well, does this give sensible answers for subregular W algebras? Does this give an S matrix in fusion rules that we'd kind of expect for something for a subregular W algebra conformal field theory? So to see where this goes, we can start with our first example from before. N is equal to 1, and we take K to be a level of this form. So again, I remind you, this is what's known as a non-degenerate admissible level for SL2. Here we take the module category to be that of weight modules with finite dimensional weight spaces. And I do just want to note here that we have what's known as spectral flow, which is a certain automorphism of a certain nice automorphism of SL2. Now, the classification of simple objects was first kind of hinted at by Adamovich and Millas, and then completed by Rideau and Wood in 2015. And the simple objects in W can be written down as follows. They're spectral flows applied to some highest weight modules, and spectral flows applied to these funny modules D, J, mu. And these are kind of relaxed modules. So here we have to, so mu is an SL2 weight. And if I fix an SL2 weight, I can pick any J value, but 2 J values will give me a reducible module. So these are kind of points of degeneration. There's a continuous spectrum of simple modules for these DJ mus, but we have to remove 2 points. And in fact, when we look at those 2 degenerate points, this relaxed module is actually indecomposable as well. So that makes it very clear that W is as not rational as possible. It has infinitely many simples and it has reducible modules. So because we only really have one family here with the kind of continuous parametrization, we'll call those the standard modules. Now we want to continue with the standard module formalism. We want characters, we want an S matrix, we want fusion rules. So in this case, we can actually do this by hand, and that's indeed what was done by Kreutzig and Rideau. You can kind of, it's not too hard to actually just work out these fusional or these characters, but there is a neat way, which is using our embedding from before. And the idea is, well, if I take a Verasoro minimal model module and some pi module, take the tensor product, that will be a module for A1UV for the SL2 by a restriction. So what we want to see is, can we realize this relaxed module as a tensor product? And what ends up working is the following. So there are only finitely many Verasoro minimal model modules. So there's only finitely many choices there. And only certain pi modules give positive energy Z-graded modules for SL2. So we're kind of hamstrung by our conditions. So the only things we can possibly form are minimal model module tensored with these pi -1Js And as it turns out, this is actually isomorphic to this relaxed module. And because this embedding is so nice, it's conformal, J gets mapped into pi on its own, the character actually splits up. So we define the character in the following form. This y to the k is just some kind of modular fudge vector. But essentially what we get is we get a lattice algebra character whose string functions are characters for the regular. And then some kind of algebraic manipulations. You can express the characters of the spectral flows in terms of the original characters. That's not too hard. And then on these characters of standard modules, one can define an action of S. And we get a modular S matrix of the following form. So if you take the character of rho L dj mu and express it in terms of rho L prime dj prime mu prime, we get some kind of coefficients. And understandably, because we get a Virasoro character here, we get a Virasoro minimal model here, but minimal model S matrix here. And then because we have also this kind of lattice data, we have an exponential term, and this exponential term, as it turns out, only contains the lattice data. So the spectral flow actually doesn't really see Virasoro. The spectral flow only changes pi negative 1j. So L is part of the lattice data. And what we're kind of seeing is a bit of a pattern here is that these relaxed modules or standard modules are acting as vehicles, and they are the ones that are pulling up this modular data in a sense. These SJ mu, these Virasoro S matrices are being smuggled into SL2 by the standard modules, which we construct by this inverse embedding. Then you can, so what Kreutzig and Ritter did is they just continued the standard module game and computed the growth and diffusion rule. And it looks like the following. So we get this kind of, this is a little bit more, it's a little bit complicated, but there's a few kind of features that we want to look at here. First of all, we get some Virasoro fusion rules, which is nice. So these are all positive integers or non-negative integers, which is great. We get this kind of symmetric looking term on the top and something on the bottom that looks somewhat related to the fundamental representation in some way. So this is a bit of a weird way to write this compared to what Kreutzig and Ritter did, but this is merely suggestive of a pattern that looks like it holds. And in this paper, they computed the other fusion rules and kind of an analysis of this lifting. So when we get genuine fusion rules, so we can continue. So let's look at n is equal to 2, which is our second example from before. We can consider again a category of weight modules with finite dimensional weight spaces. Again, BP has a spectral flow automorphism. And again, we can classify simple objects. So this was done by myself, Kazuya Kosetsu and David Ritter in 2020. And the classification superficially is identical to the SL2 classification. We get spectral flows of highest weight modules, and we get spectral flows of some relaxed modules. And here, instead of having kind of 2 excluded values for J, we have 3 excluded values for J. So SL2, 2 degenerate points, SL3, 3 degenerate points. Getting some patterns. So again, yeah, I didn't mention it in the SL2 case, but these highest weight modules sometimes have infinite dimensional top spaces, but that's life. So again, we only have one family really here of modules that have a kind of a continuous family of modules. And we'll say that the second family of modules are precisely our standard modules. So in particular, we want to kind of observe here that our standard modules actually includes some reducible modules. And that's actually kind of important a little bit later on. So in this case, we want to do the same thing as before. In this case, it's not as easy to just kind of write down the characters by hand. So we want to use our trick from before. So we have this embedding of BPUV into the W3 minimal model tensor pi. And we want to see, can we realize this relaxed module as a tensor product? I do understand this is all kind of sounding like I'm repeating myself, but that's sort of the point. So this kind of thing was first suggested by Adamovich, Kosetsu, and Ritter, and I'm currently writing up a paper with David Ritter about this now, where we flesh this kind of modular picture out. And the idea is exactly as before. W3UV only has finitely many modules. Only certain pi modules give positive energy Z-graded BP modules. So we are kind of restricted in what modules we can form. We can take these minimal modules, these regular modules, and these pi -1 modules. This is kind of the only thing we can do. And as it turns out, this is precisely these relaxed modules from the classification. Now, we have to pick our modular fudge factor a little bit carefully here. But in essence, again, the embedding is so nice that the character decomposes into a lattice vertex algebra character with string functions given by regular W algebra characters. And again, we can do it. It's kind of an easy exercise, but it's a bit of a straightforward calculation to express the characters of the spectral flows in terms of the characters of these relaxed modules. That's not too bad. But here there is a bit of a sticking point, namely that these characters, these W3 characters are not linearly independent. So in essence, these characters don't really specify the relaxed module in the way that we want for the purpose of modularity and fusion rules. If you want, there's an automorphism there's a kind of a conjugation automorphism of W3, which preserves the characters but does not preserve the module. So in principle, if the W0 eigenvalues are non-zero, this tends to make this thing a bit hairy. But there is a fix for this. So this fix was kind of innovated by Tomoyuki Arakawa and Jethro Vernecker. And there what they do is, instead of considering W3 characters, we think about W3 one-point functions. Then these one-point functions have the modular properties. They're generically linearly independent, and they have the modular properties that they should. And in essence, what we can do here is it's a bit of a technical band-aid, but we can, whenever we see a W3 character, there is a systematic way that we can upgrade that to a one-point function in such a way that we get linearly independent characters. Then on these so-called, maybe we can call them upgraded characters, or these new characters of standard modules, we can again define a modular S matrix. And it looks like the following, which is great. It is a W3 S matrix, which is the data of this character here, multiplied by some exponential term, and that exponential term carries all the lattice information. Again, spectral flow here, if I take the spectral flow of Rj mu, it only actually changes the pi module part. It misses W3 completely. And again, we see this nice property that these standard modules are acting as vehicles, driving up the modularity in fusion rules. And again, we can turn the standard module crank, which is what we've done, and compute growth and diffusion rules. So in this case, it's a bit ugly. So I will say is that I'm going to say that this first term is symmetric. It is once you apply spectral flow to the half, but so this becomes +3n2 and -3n2 on the top. So the growth and diffusion rule, all the coefficients are non-negative integers, which is great, which is what we want from physics. And we see that we have the same pattern as before. We have some symmetric term on the top, and then some kind of correction terms on the bottom, but these correction terms in some way are related to fundamental representations of SL3 this time, which is quite neat. I don't quite understand exactly why this is happening, but it's there and it exists. So for n is equal to 1 and 2, I want to now kind of, we want to see what we can work out about SLN now. So now we know n, we know SL2, we know SL3. What about SLN plus 1? In both the n is equal to 1 case and n is equal to 2 case, the classification kind of works by, you can use U, you can do highest weight module things using quantum Hamiltonian reduction, using various results of Arakawa and Katsumoto. In fact, what's kind of sneaky here is that the only reason that the n is equal to 2, so the Beshadsky-Polyakov classification really works, is not because Beshadsky-Polyakov is a subregular W algebra, but it's because Beshadsky-Polyakov is a minimal W algebra. And minimal W algebras, the highest weight theory is much more fleshed out compared to subregular. In fact, there isn't a huge amount of information about highest weight modules for subregulars. So at this point, it's a bit unclear how to do this classification step. So in a sense, we don't really have modules to realize. So instead of realizing modules by this tensor product construction, we're just going to define them and use them on their own. So in essence, we do exactly what we did before. This regular W algebra minimal model has finitely many modules. There are only some pi modules that give positive energy Z-graded modules. We are kind of forced into taking this tensor product. And these tensor products will be relaxed modules with a continuous parameter. And this is kind of a very sketchy schematic of what these things look like. And again, from these embedding results, we know that these are almost simple. So all singular vectors need to live on this top space. There's an upper bound on the number of degenerate points, so the number of values of J for which these things are reducible. So again, we saw before we had 2 for SL2, 3 for SL3. So we get at most n plus 1 for J. I believe this can be upgraded to exactly n plus 1, but that's a little bit more work. And again, we want to do pretty much what we did for n equals 1 and n equals 2. We want to take spectral flows of these relaxed modules, call them standard modules, find the next matrix, find some Griffin diffusion rules. We can define a spectrophotomorphism. It's using these nice intertwining operators defined by Lee many years ago, I think in the 90s. And again, we'll tentatively call spectral flows of Sj mu our standard modules. And again, I remind you, the Sj mu's are precisely these tensor products, which is what we saw before. So these are sometimes reducible, but almost always simple for generic values of J. And what we found, or what I'm currently writing up into a paper, is the following. We have to set our fudge factor in a particular way. This LNK is actually so the JOPE is some number over Z minus W squared. The some number is actually LNK. So this is sort of related to the field J. Because this embedding that we defined earlier is so nice, the character splits once again over the tensor product components. And again, we get the same behavior as before. We get a regular W algebra character appearing as kind of string functions with respect to these lattice algebra characters. The translation to characters of spectral flows is algebraic and not too much work. And again, we have this linear independence problem. And again, we suspect, or we conjecture that we can do this upgrading procedure here. And modulo that thing being spelled out, we can define an action of SL2Z on these new characters. And no surprises at all. We set this funny gamma factor. The S matrix corresponding to these standard modules is exactly the S matrix for the regular multiplied by an exponential term that captures all the lattice information. So once again, spectral flow does not care about the regular. It only hits pi. It only changes the pi component. So it's part of the pi data. And again, the standard modules are lifting this information from the regular up into the subregular. So it's going. So these relaxed modules really are mapping information from a rational VOA up to a non-rational VOA. Now, the next step is Griffin diffusion rules. This is hard. The main reason this is hard is because the continuous Villander formula has as its denominator an S matrix corresponding to the vacuum. The vacuum is the highest weight module, and as I said before, highest weight theory for the subregular W algebra is not particularly clear. So precisely how to work out this coefficient is a bit tough. But this is necessarily the next step. So hopefully when this in preparation over here is replaced by an integer greater than or equal to 21, I'll have some more substantial things to say about that calculation. So as far as future directions go, we could think about subregular W algebras outside of type A. So seeing how straightforward the type A case is, that kind of suggests to us that the other cases should be more or less the same. but they still need to be kind of worked out by hand or maybe case by case. We can think about how to generalize this approach to all. So we now know how to do one inverse reduction. We can think, well, can we do other inverse reductions now? That's a bit more tricky, but that's kind of another thing to look at. Another thing to, if we stay in the world of subregular W algebras in type A, we kind of worked out all this stuff for non-degenerate admissible levels, at least all this modular and fusional stuff. All the embedding results are for whatever level we want. But we can ask the question about degenerate admissible levels for subregular W algebras. So these are the ones for which this embedding of simple quotients doesn't exist. These are hard. For Bichetski-Polyakov, the degenerate admissible levels are when the denominator V is 1 or 2. When V is 1, these are non-rational, and these are kind of spelled out by Drazen Adamovich and Anna Kontrek. And when V is equal to 2, this gives us an exceptional W algebra, which is rational. And another, in a bit of a different direction, I think I might have mentioned before that this inverse reduction is known for finite W algebras. So if we take an affine W algebra, its U algebra is a finite W algebra. And in the finite world, partial reduction is known. It was defined by Stefan Morgan in his PhD thesis. So, and then what us as the affine people can say is, well, we now know, hopefully if I can write this up in a good amount of time, that the partial reduction is somewhat understood in some sense. So the finite reduction, the finite W algebra people don't know how to do inverse reduction, but we don't know how to do partial reduction. So this is an opportunity for finite W algebra people and affine W algebra people to meet in the middle and combine the respective information. But that's all I have for today. Thanks everyone for listening, and I'm happy to answer any questions if any of you have any. Thanks again.
Thank you, Zach. Let me stop the recording. Thank you so much. If you have questions for Zach,